couple of sessions and we've matured into rudiments of capacitors. Hopefully you would have gone through the stuff that I've already covered, would have also looked through some examples from a text and got yourself acclimatized. I'm also assuming that you would have at least looked through some of the problems that were there in the previous sheet. But even before I go bang on the sheet, I'm going to just add a few more remarks to capacitors. So we've primarily looked at parallel plate capacitors, air and dielectric, and related stuff. Now I'm going to show you a cylindrical capacitor, two coaxial cylinders, infinitely long, infinitely long. Very long. Now, hello? Common axis, two coaxial cylinders, very long. Charges on the curved surfaces of the two cylinders, and let's say lambda is the charge per unit length, lambda and minus lambda, in the sense that, you know, one terminal of the battery would be connected to the inner cylinder, one terminal of the battery would be connected to the outer cylinder. So if one has charge per unit length lambda, the other one would have charge per unit length minus lambda, right? Because charge on one would be at the expense of the other one when they are connected. And let's say the region between these two cylinders is air. So cylindrical capacitor with two coaxial cylinders, and there is electric field between the two cylinders. In the air region between the two cylinders, there is an electric field, right? Now, when these cylinders are very long, we don't talk of the capacitance of the entire cylinder. We talk of capacitance per unit length of the cylinder. We talk of capacitance per unit length of the cylinder. We are seeking to compute capacitance per unit length. So if this is charge per unit length lambda on this, and this is charge per unit length minus lambda on this, and let's say the inner cylinder has radius small a, the outer cylinder has radius small b, right? We are then talking of the potential difference between these two cylinders, right? We're talking of potential difference between these two cylinders, and then charge per unit length divided by potential difference between the two cylinders will give you what? The capacitance per unit length. The capacitance per unit length would be obtained when you take charge per unit length lambda divided by the potential difference between the two cylinders. Now, why would there be a potential difference? Because there is an electric field. Now, from symmetry, again, electric field in this region, in the annulus between the two cylinders, air region between the two cylinders, that's what is important, right? Now, for the sake of points outside the cylinder, from symmetry considerations, this lambda could be imagined to be on the axis. This lambda could be imagined to be on the axis. Then if that means charge per unit length on the axis, then the electric field at a distance r from the axis, the electric field is going to be lambda by 2 pi epsilon naught r. The electric field is going to be lambda by 2 pi epsilon naught r. Just like when you have a spherical conductor with charge uniformly distributed on the spherical conductor, for points outside the conductor you can imagine the charge to be concentrated at the center. Similarly, if you have a charge uniformly distributed on the curved surface of a cylinder, then for points outside the cylinder you can imagine that charge to be on the axis of the cylinder. So then lambda by 2 pi epsilon naught r is the electric field from the positive to the negative charge, right? Now when you move a distance dr in this direction, this is E, the electric field at a distance r, then if you move in the direction of the electric field at distance dr, then the fall of potential, the drop of potential, the potential drop is given by E at r into dr. That's a potential drop. When you move a distance dr in the direction of the electric field, the potential decreases by this amount. Yes or no? So what we need is the total potential drop from cylinder 1 to cylinder 2. The total potential drop from cylinder 1 to cylinder 2 would be the sum of the potential drops, where r runs from A to B. Yes or no? That's going to be the potential difference. That's going to be the potential difference between the two cylinders, 1 and 2. Right? Replace ER by lambda by 2 pi epsilon naught r and supply the limits. This would become lambda by 2 pi epsilon naught. 1 by r dr would be log r. So log B by A. 1 by 2 pi epsilon naught log B by A would be the potential difference. Now lambda is the charge per unit length. So lambda divided by V would be the charge per unit length divided by the potential difference. And charge per unit length divided by the potential difference is going to give me capacitance per unit length. So the capacitance per unit length is going to be given by charge per unit length divided by the potential difference. Charge per unit length divided by the potential difference. That's going to give me capacitance per unit length. Now very clearly, this then lambda divided by V turns out to be 2 pi epsilon naught divided by log B by A. That's the capacitance per unit length of two coaxial cylinders. Got me? So that's a result you want to keep a tab on. If this region is filled with a dielectric of permittivity epsa, then this will become epsa naught epsa. This will become epsa naught epsa. This is what would happen. Clear? Can I wipe this off? Now let Gauss's law, right? Electric field, okay, at this point will be created only by this, isn't it? Gauss's law. So let me tell you, I have done this calculation for you in the past, but let me quickly do that one more time for you. Computation of the electric field at the point where he said, hey, have I made life simple for myself? See, for the inner cylinder, you could imagine charge to be on the axis of the cylinder, right? Charge per unit length, lambda on the axis of the cylinder. This is the outer cylinder. The charge per unit length here is minus lambda, right? Now what you can do is, outside the inner cylinder, you construct a Gaussian surface, cylindrical Gaussian surface, cylindrical Gaussian surface of radius r greater than a. That means it will be in the intervening region, r greater than a. Right? Say this is 1 unit length of this cylinder. 1 unit length of this cylinder. That means the total charge here would be lambda. Right? Now, from symmetry considerations, electric field at every point of the curved surface would be radially outwards. Would be radially outwards and would be uniform. Yes or no? Therefore, it will be in the direction of the area element at every point of the curved surface. So, if E is the electric field at a distance r, then the total flux passing through this passing through this cylindrical surface of radius r is going to be E into 2 pi r L. L is 1. Yes or no? E into 2 pi r is the total flux because of this, right? And that must be charge enclosed, which is lambda by epsilon naught. So the electric field at a distance r, like I mentioned, was lambda by epsilon naught r. Got me? No confusion now? So that's simply out of Gauss's law. Now let me look at another variation. Two spherical capacitors, two spherical conductors, one at center C1, center C2, two spherical conductors, and the distance between their centers is d. The distance between their centers is d. One is of radius a, the other one is of radius b. We will eventually assume that d is much larger compared to a, d is much larger compared to b in our final calculations. Now when I connect the two spherical conductors with the help of a battery, then let's say charge plus q would accumulate on one, charge minus q would accumulate on the other one. Charge q would accumulate on one and charge minus q would accumulate on the other one. Now, I want to compute the potential difference. Starting from here to here, I want to compute the potential difference. And then Q divided by potential difference would be the capacitance of this arrangement. Q divided by the potential difference between the two cylinders is going to be the capacitance. So now, if I look at a point P at a distance r from C1, then the electric field here is, because of this, is going to be kq by r squared. Because of this is going to be kq by r squared. Yes or no? The electric field at P, because for all points outside this, you can imagine q to be at the center. So kq by r squared is the electric field because of this. Now, because of this, for at the point P, which is now at a distance d minus r from C2, at a distance d minus r from C2, the electric field at P is going to be k times minus q by d minus r whole squared this way. Yes or no? At P, because of this, I can imagine minus q to be at the center C2. So the electric field is going to be in this direction, k times minus q divided by d minus r whole squared. Yes or no? K minus q by d minus r whole squared in this direction is the same as kq by d minus r whole squared in this direction. Yes or no? So instead of dealing with this direction, I say it's like kq by d minus r whole square, like this. That's a net electric field at P. That's a net electric field at P. Yes or no? Now I can remove this. Now the electric field is from left to right. Electric field at R. Right? And it's varying. So I need to compute the potential difference between these two spheres. So if I go dr units in the direction of the electric field, then the potential drops by an amount er into dr. Right? So moving dr units from left to right will cause a potential to drop by kq by r squared plus kq by d minus r whole square dr. Right? The total potential drop from this point to this point, from this point to this point, is going to be sum of all of this, where r runs from A all the way to this point, but this point is r equal to d minus b. This point is d minus b, isn't it? This distance is d minus e. So r runs from A to this point, which is d minus b, right? A to d minus b. That's the potential difference between the two spheres, right? Then Q by V will give me the capacitance of this arrangement. Q by V will give me the capacitance of this arrangement. Let's see how much it turns out to be. Okay, see, when I integrate this, I get minus 1 by R. So minus KQ by R. So minus KQ 1 by R. R runs from A to D minus B. This part? Yes or no? When I integrate this, then this will give me KQ 1 by D minus R. R runs from A to D minus B. I hope you understand whatever I have done here. I hope 1 by d minus r whole squared, when you integrate with respect to r, will give you 1 by d minus r. Yes or no? No? Not sure about this, right? Now let me supply the limits and see what it turns out to be. So the potential difference V will turn out to be minus KQ into 1 by d minus b minus 1 by A for this, then plus KQ. When R is D minus B, this will become 1 by B. When R is D minus B, this will become 1 by B. When R is A, this will become D minus A. D minus A. Yes or no? Right? Now, V by Q would be 1 by capacitance. V by Q would be 1 by capacitance. So I bring in this Q right here so that I get 1 by the capacitance of this arrangement. 1 by the capacitance of this arrangement. So, can I remove this part? One by C is K times, K is 1 by 4 pi epsilon naught, 1 by A plus 1 by B minus 1 by D minus A minus 1 by D minus B. That's the reciprocal of the capacitance of this arrangement, right? Now, if D is much larger compared to A, and D is much larger compared, till this point I have not used any approximation, I have done the actual calculations, right? But if D is much larger compared to A and if D is much larger compared to B, then D minus A could be looked upon as D, D minus B could be looked upon as D, right? So this, if D is much larger compared to A and D is much larger compared to B, will turn out to be K into 1 by A plus 1 by B minus 2 by D. Right? That's the capacitance of this arrangement. Clear? There is another way you could have done a calculation on capacitance of this arrangement. Can I wipe this off? Without even taking recourse to the electric fields here. Okay, let me look at the total energy of this. Let me look at the total energy of this. There is self energy here, there is self energy there, and there is interaction energy. That's the total potential energy of this arrangement, right? The total potential energy of this arrangement is potential energy of this, which is kq squared divided by 2a, k minus q whole squared divided by 2b, right? Remember this result of self energy, right? And then there is interaction energy. For interaction energy, imagine this q to be a point charge here, this minus q to be a point charge here, then kq minus q divided by d, kq minus q divided by d, that's the interaction energy. So kq minus q divided by d. Yes or no? Now, if C is the capacitance of this arrangement, then the total potential energy should be q squared divided by 2c. Q squared divided by 2c. There you go. Q squared would get cancelled and you can calculate 1 by C equivalent. See, 1 by C equivalent becomes K into 1 by A plus 1 by B minus 2 by D right away. Do you see that? Right away you get that. Nay? Potential energy is Q squared by 2 times the capacitance. So 1 by C equivalent becomes, this 2 comes here, K into 1 by A plus 1 by B minus 2 by D, a result that we got out of lot more effort. Yes or no? Really? Interaction energy? Why? Energy can't be negative. I'm not calculating kinetic energy. This is potential energy. Can it not be? It's K Q1 Q2 divided by the separation, the interaction energy. No? Tell me one place where I said mod. Oh God. No? Of course not. Never on one occasion did I say it will be mod. Certainly not. These are not kinetic energies. These are potential energies. They could be positive, negative and zero. K Q1 Q2 divided by R would be the interaction energy. Right? So far so good, right? Now, an isolated sphere, if I had an isolated sphere, right? Then for an isolated entity, the manner in which we compute capacitances, suppose this is a sphere of radius r, and if a charge q is assigned to the sphere, and which results in the sphere getting raised to a potential V, then the capacitance of this arrangement is given by Q by V, right? That's how you compute the capacitance of isolated entities on prescribing or assigning a charge Q to that entity. If its potential gets raised to an amount V, then Q by V is the definition of the capacitance of an isolated entity, right? Now, if charge Q is given to this conductor, it will spread uniformly on the surface, and the potential to which this gets raised is going to be KQ by R, right? And therefore Q by V would be R by K. Q by V, which is the capacitance of the arrangement, would be R by K, which is 4 pi epsilon naught R, is the capacitance of an isolated sphere, right? Two concentric spheres now, clear? Two concentric conducting spherical shells, one of radius small a, the other one of radius small b. Coaxial is for cylinders, concentric is for spheres, right? For shells, common center, we don't talk of an axis, common axis, right? O is the center, and if the two are connected by a battery, then one would gather charge Q, the other one would gather charge minus Q, one at the expense of the other. It does not matter which one is plus Q, does not matter which one is minus Q. So if this is the charge Q that accumulates on this, then this must have lost charge minus Q. And there is electric field in this region. The whole idea is whatever lies here. Right? So eventually then, what's the charge that must have flowed through the battery to produce this charge disposition? Q. Divided by the potential difference between the two spheres would be the capacitance of the arrangement. Right? Now, potential of the inner sphere. Because of its own charge, KQ by A. Right? Now, imagine this charge minus Q. This charge minus Q produces on itself a potential K minus Q by B, and that's a potential it produces anywhere inside. Therefore, this minus Q at this point on the inner surface would produce a potential K minus Q divided by B. Yes or no? What is the potential on the outer surface? Because of its own charge, K minus Q divided by B. Because of this, for all points outside this, I can imagine this Q to be concentrated at the center. Divided by B. Yes or no? Wow, very melodious. Whose was that? Ringtone. Whose was that? It's just an interesting ringtone. Very different from the ones that I have seen in the recent past. Just curious. Would you like to share that ringtone with me? Oh, yes, Vedic man. Vedic. God. If I was given one choice to choose whose it was, I would have selected you anyways. Chalo. Now, the potential difference between the two, Vi minus V naught. is going to be KQ into 1 by A minus 1 by B. That's a potential difference. That's a potential difference V between the two. Yes or no? If you subtract, this is what transpires. Right? Then the capacitance is going to be Q divided by V, the charge that has flowed through the battery, divided by the potential difference between the two shells thus produced. So Q by V is the capacitance of this arrangement of a pair of concentric shells, and that is very clearly 1 by K into 1 by A minus 1 by B. Yes or no? 1 by K is like 4 pi epsilon naught. If B tends to infinity, this will become an isolated sphere. If B tends to infinity, this will become 0, and this will become 4 pi epsilon naught A. Isn't it? It will reduce to the previous situation if B tends to infinity. So whenever you're talking of an isolated conductor, it's as if the other conductor is at infinity. It's as if the other conductor is at infinity. Its pair is at infinity. This is what it really means. Got me? Some problem solving. Coming down to some problem solving. Refer to the sheet, but a few things which I want to communicate. One, you're going to encounter time and again an arrangement of this kind. Say C1, an arrangement of this kind. Hello? A and B could be connected to the terminals of a battery. A and B could be connected to the terminals of a battery. Now, I want to find the condition so that the potential of P becomes the same as potential of Q. Potential of P becomes same as potential of Q. When A and B are connected to a battery, I want to find the condition so that P and Q are at the same potential. P and Q are at the same potential, right? Now, so if they're connected by a battery, then let's say charge Q flows through the battery. Charge Q flows through the battery. It comes to A. Charge Q comes to A. That means from B, it flows past the battery, which is here. This could be the battery, for example. Charge Q flowing, right? Q comes down to this point, and this is say C3, this is C4. And Q gets delegated in two directions. Q1 deposits on this plate, and Q3 deposits on this plate, say. Yes or no? Now, if there is Q1 here, there is going to be minus Q1 induced on this, right? And this portion, these two plates are electrically isolated. The net charge they carried was 0. So if this is minus Q1, how much this must be? Plus Q1. If this is Q3, how much must this be? Minus Q3. These two plates are electrically isolated. So if this is minus Q3, this must be plus Q3. If this is Q1, this then must be minus Q1. This then must be minus Q3. That means these two plates would have together lost charge Q1 and Q3, Q1 plus Q3, which flows past B, which is equal to Q. Q is Q1 plus Q3. And leaving these two deprived of charges Q1 and Q3. This is the charge arrangement. Yes or no? Now this point is electrically the same as A, right? Very clearly, since P and Q are at the same potential, the drop from A to P is the same as the drop from A to Q, because P and Q are electrically the same, being at the same potential. The potential drop from A to P must be the same as potential drop from A to Q. Yes or no? Right? Now, the potential drop from A to P is like the potential drop across this capacitor, which is like charge on the first plate divided by C1 is the algebraic potential drop. So, Q1 by C1, right? And that must be the same as the drop from A to Q, which is drop across the plates of this capacitor, which is charge on the first plate divided by C3. So that must be Q3 by C3. Yes or no? Does it make sense? Now, this point and this point are electrically the same, right? The drop from, and P and Q are at the same potential. So the drop from P to B must be the same as drop from Q to B. What's the drop from P to B? That's the drop from this plate to this plate, which is algebraic charge on the first plate divided by C2. So that makes it Q1 by C2 equals the drop from Q to B, which is Q3 by C4. Yes or no? These are two conditions that will force P and Q to be at the same potential. Divide this by this, you end up getting C1 by C2 equals C3 by C4 is what you get when you divide. That will cause P and Q to be at the same potential. Yes or no? Which is the same as C1 by C3 to be the same as C2 by C4. C1 by C3 to be the same as C2 by C4. That means if this by this capacitance by this capacitance is this capacitance by this capacitance, then and A and B are connected to the terminals of a battery, then the potential of P must be the same as potential of Q. Potential of P must be the same as potential of Q. That means if P and Q are at the same potential and you connect a resistance across P and Q, there will be no current flowing through the resistance because the ends are at the same. If you connect a capacitance C here between P and Q, and if C1 by C3 is C2 by C4, P and Q will be at the same potential. The potential difference between these two plates will be 0. Therefore, the charge on these two plates would be 0. And therefore, this would have no impact. The presence of a capacitance between P and Q will keep the circuit passive as far as any exchange between P and Q is concerned. No electrical exchange between P and Q gets ever executed if P and Q are at the same potential. And when are P and Q at the same potential? If C1 by C3 is C2 by C4. Then connect any electrical element between P and Q. That electrical element will remain oblivious of anything that is happening in the circuit. Right? So, if you, whether now there is a capacitor or there is no capacitor between P and Q. If P and Q are at the same potential, put a capacitance or a resistance or anything. That or without it will mean the same. You can even, if there is a capacitance and P and Q are found to be at the same potential, you can remove the capacitance because it doesn't have an active impact on the circuit at all. You know what I'm saying? And when P and Q are at the same potential, this is said to be a balanced Wheatstone network between A and B. It's said to be a balanced Wheatstone network between A and B. If Vp is the same as Vq, then it's a balanced Wheatstone bridge. Across AB, across terminals A and B. This is said to be a balanced Wheatstone bridge. Are you all okay with this? Now, to illustrate this, I will take recourse to some number problems in the sheet. Please refer to the sheet. Please refer to the sheet. Can I wipe this off, and are you okay with all of this? P and Q, when would they be at the same potential? If C1 by C3 is C2 by C4. Then whether you have a capacitance between P and Q or you don't have a capacitance between Q, it's a same circuit that we are talking of, right? So in the event somebody gives you a capacitance, you can remove that capacitance, brush it aside, ignore it with cold command, right? Can I wipe this off? Now, this fact is sometimes heavily deployed towards computing equivalent capacitance across. If you identify a balanced Wheatstone network between 2 points, then you know you can carry out an execution of that circuit with a great amount of ease. Let's look at a few problems here. Okay, let me look at number 5, 2 part 5. Part 5. Let me look at 2 part 5. I want to find the equivalent capacitance of this arrangement between points A and B. I want to be able to find the equivalent capacitance of this arrangement between points A and B. Now in these cases, see, the only smartness that you need to develop is learning how to redraw this circuit. Learning how to redraw this circuit between P, A and B so that it is brought to a topologically known format. Familiar looks are brought in. That's the whole idea, right? What you do is, let me call this point P. Let me call this point Q. Let me redraw the circuit. Let me redraw the circuit between points A and B. Okay. Now, there is a point A which is connected to one terminal of the battery. All right. And there is a point P. Between A and P, there is a capacitance which is 4 microfarads. This is the point P. Between A and P, there is a 4 microfarad capacitance. There is a 4 microfarad capacitance, right? Now, there is a point Q. This is the same as A, right? This is the same as A. Between A and Q also there is a 4 microfarad capacitance. So between A and Q, this is Q, there is a 4 microfarad capacitance. Clear? Right? But between P and Q there is a 10 microfarad. Between P and Q there is a 10 microfarad. Now comes the point B. Now comes the point B. Realize between P and B there is a 4 microfarad capacitance that connects P to B. Yes or no? So between P and B there is going to be a 4 microfarad capacitance. Clear? Between P and B, this one. And between Q and B, there is going to be a 4 microfarad capacitance between Q and B. Yes or no? Now between A and B, I want to find the equivalent capacitance. Look, 4 by 4 is the same as 4 by 4. Therefore, P and Q must be at the same potential. Yes or no? It's a balanced Wheatstone bridge between A and B. So whether that means this capacitance or this electrical element is non-existent, whether it is there or not there, it's not going to have any impact. So might as well remove this. Now once I remove this, life becomes so much rosier, because now all that we have is this 4 and this 4 in series. This 4 and this 4 in series will give me 2 microfarad, and this 4 and this 4 in series will give me 2 microfarad, and this 2 microfarad in parallel with this 2 microfarad will give me 4 microfarad. Yes or no? You know what I'm saying? This 4 and this 4 in series gives me 2 microfarad. This 4 and this 4 in series will give me 2 microfarad, and this 2 microfarad in parallel with this 2 microfarad will give me 4 microfarad. So what's the equivalent capacitance between A and B? 4 microfarad. Do you realize that the balanced Wheatstone bridge came in so handy? Realize that? Is that okay or not okay? Right? Nilesh, all of you understand this? Okay, let me illustrate a little more. Can I wipe this off if you're done? Look at 2 part 2. Right. I now want to be able to find the equivalent capacitance of this network between points A and B. This is what I want to be able to do. Clear? Again, see, once you mature a little more, then you will not have to redraw the circuit. But in the initial stages, when you're still trying to get acclimatized to variations here, it is recommended, very strongly recommended, that you redraw the circuit, and with guidelines that I'm prescribing with the aid of these problems, right? Now, see, this is A, electrically, all these are the same as B. These are all the same as B. They're directly connected to B. Electrically, they are referred to as B only. Now, if this point is P and this point is Q, right? Let me redraw the circuit between A and B in a more systematic manner, right? From A to P, there is a capacitance, and from A to Q, there is another capacitance. So I label a point A and a point P, which is like this. Between A and P, there is a capacitance, and then between A and Q, there is another capacitance. So there is another capacitance. Okay. Then between P and Q, there is a capacitance C, right? So between P and Q, there is another capacitance C, right? Now, Q to B goes a capacitance C. So from Q, you have a point B here. From Q to B, there goes a capacitance C. Right? Yes or no? Am I confusing you? From P to B, there is another capacitance C. And between A and B, there is a capacitance C here. Right? So between A and B, there is a capacitance C. Between A and B, there is a capacitance C. That's the arrangement. Now, look at this between these 2 points. Just look at this. This by this, which is 1, C by C, and this is C by C1. So P and Q must be at the same potential. And if P and Q are at the same potential, then does this matter? So can I remove this? So let me disentangle this, because its presence or lack of it has no consequence. It is only adding to dirt and clutter. Clear? All right, now this C and this C in series. So that will make it C by 2. Right? This C and this C in series. That will make it C by 2. Yes or no? C by 2 in parallel with C by 2. That makes it C. And this C in parallel with another C. That makes it 2C or not to C. You know what I'm saying? I'll repeat. Anyone who wants me to repeat? Nahi? Clear? You see that? 2C is the capacitance between A and B. See how easily the problem gets sorted and solved, because you identified this as a balanced Wheatstone bridge. You identified this as a balanced Wheatstone bridge. Life becomes so much more simpler, right? But not that real life will always present balanced Wheatstone bridge. There could be times when the bridge is not balanced, when C1 by C2 is not C3 by C4. Therefore, we must have solutions to more intricate situations as well. We will then have to deploy first principles to obtain capacitance between points A and B if C1 by C2 is found to be not equal to C3 by C4 and Vp is not equal to Vq, and the presence of this capacitor between P and Q is of consequence. Right? Can I wipe this off and then get you into a little more involved stage? Clear? Can I wipe this off? Now, look at 2 part 1. Look at 2 part 1. All right. I'll change the shape. Right. I now want to be able to find equivalent capacitance between points A and B. I now want to be able to find equivalent capacitance of this network between A and B. Hey, realize that P and Q are not at the same potential. Why? because 1 by 2 is not the same as 1 by 1. So it's not a balanced Wheatstone bridge. So then this capacitance has an active role to play. I cannot forget all about it, right? How does then one, in a very general sense, find equivalent capacitance between any 2 points in an electrical network? Using this, please switch it off. Using this, I'm going to communicate a very generalized way of finding equivalent capacitance between points A and B. Right? Let's see how to handle this. So what you do is, essentially, between any 2 points in an electrical network, if you are seeking to find the capacitance between any 2 points in an electrical network, if you are seeking to find the equivalent capacitance, what you must do is imagine between those 2 points a hypothetical battery to be connected. Imagine a hypothetical battery to be connected. Does not matter how much is V. This is a hypothetical battery connected between these 2 points A and B. And if this connection leads to a flow of charge Q through the battery, if this connection leads to a flow of charge Q through the battery, then the capacitance between A and B is the charge flowing through the battery divided by the EMF V of the battery. That's a generalized way of looking at capacitance between any 2 points in any electrical network, no matter how complicated that is. You connect those 2 points with the help of a battery. The charge flowing through the battery divided by the EMF of the battery V will give you the equivalent capacitance between those 2 points. This is how it goes. Right? Now let's see how to do this. So what I'm going to communicate would then be a very generalized way of finding equivalent capacitance. If you have not encountered symmetry, if you have not encountered balanced Wheatstone bridge, then you know the largest amount of complication that you can encounter is what I'm going to do next. Right? Now, if this charge Q flows through the battery, this charge Q results in, say, Q1 coming here and Q2 going there. Q is Q1 plus Q2. Q is Q1 plus Q2. Right? If you have Q1 here, what would you have here? Minus Q1. Right? Now, these 3 plates, this plate, and this plate are electrically isolated. Together, they had no net charge at any point of time. They will continue to have no net charge. The net charge is going to be 0. It's going to be 0. So out of this, what I assume is, let's say a charge Q0 accumulates here. Say a charge Q0 accumulates here. Then the charge here must be Q1 minus Q0. Why? So as to cause the net charge of these 3 electrically isolated plates to be 0. Clear? Now, if this is Q0, how much is this going to be? Minus Q0. Right? Now, if this is Q2, how much is this going to be? Minus Q2. Now, if this is, now these 3 plates are talking to each other, this plate, and this plate, and they are electrically isolated from the rest of the world, right? So, together these 3 plates would have no net charge. So, if this is minus Q0, this is minus Q2, then this must be Q0 plus Q2. This must be Q0 plus Q2. Now, if this is Q0 plus Q2, how much must this be? Minus of Q0 plus Q2? If this is Q1, how much must this be? Minus Q1. I'm sorry, Q1 minus of, that means Q0 minus Q1. That means Q0 minus Q1, minus of this. Yes or no? Now, look at these two plates together. Minus Q0 will get cancelled with plus Q0. Then this will be minus Q1 minus Q2. That means together these two plates have lost minus Q1 minus Q2, have lost Q1 plus Q2. Together these two plates have lost charge Q1 plus Q2, which is actually equal to Q, which has flowed past the battery. Q is actually Q1 plus Q2. All charges are in supreme balance. See the balance of charges everywhere? Yes or no? Now, I am going to apply KVL to this loop, and I am going to apply KVL to this loop. Algebraic sum of the potential drops in this loop must be 0. Algebraic sum of the potential drops in this loop must be 0. So then, Q1 by 1 is the drop here, isn't it? Charge on the first plate divided by capacitance. That's the algebraic drop, Q1 by 1. Then, what's the drop from here to here? Q0 divided by 1. In this sense? Yes or no? What's the drop from here to here? No. Minus Q2 by 2 is the algebraic drop. Algebraic drop would be algebraic charge on the first plate divided by capacitance. So minus Q2 by 2. That must be 0. Yes or no? Yes or no? That gives us Q2 minus 2Q1 as 2Q0, equation 1. Yes or no? Q2 minus 2Q1 is 2Q0. Yes or no? Right? Now, let me deploy KVL to this loop as well. Let me deploy KVL to this loop, right? What's the drop from here to here? Charge on the first plate divided by 1, right? So, Q1 minus Q0 divided by 1 is the drop from here to here. Then I go here. Charge on this plate divided by 1. That's going to be the drop from here to here. Charge on this plate is minus Q0 plus Q2 divided by 1. Yes or no? That's algebraic drop from here to here. What? Am I confusing you? Then I go this way. Then drop from here to here is going to be what? Minus Q0 by 1. That must be 0. Yes or no? So that gives me, do you realize this? This gives me like a Q1 minus Q2 equals 3Q0. Yes or no? See if I made a mistake. Have I made a mistake anywhere? No? So the second equation is Q1 minus Q2 is 3Q0. If there is any algebraic mistake, fix it. Now, so far so good, right? These two are the only equations. I've applied KVL to both the loops and I've exhausted any other possibility of applying KVL anymore, right? Now what I do is, look, essentially, this is what I want to be able to do. The charge flowing through the battery, which is Q1 plus Q2, capacitance is going to be the charge flowing through the battery, which is Q1 plus Q2, divided by the potential V. Now, potential difference between A and B. This V is actually the potential difference between A and B. And the potential difference between points A and B will be the same no matter how you compute it, right? Along any path, if you compute the potential difference between A and B, it's going to be the same. Why? Because it's a conservative field. It's a conservative field. That means from A to B, I can go like this and I can compute the potential difference. The potential drop from A to B is going to be drop here plus drop here. Or I could have done this. A to B like this. Drop from A to B is going to be drop here plus drop here. Or I could have gone from A to B like this, which is going to be drop here, plus drop here, plus drop here. That's going to be V. It's going to be the same no matter what path I take. The drop is going to be the same. So then Q1 plus Q2 divided by drop. Might as well take this, right? So the drop from here to here is Q1 by 1. The drop from here to here is Q1 minus Q0 by 1. This then is going to be the capacitance, right? That's a basic idea. That's the framework. That's the backbone. Now to perform the last rites, which is ordinary algebra. What I want to do is, see if I can write both. So this is 2Q1 minus Q0. This is 2Q1 minus Q0. Can I find Q1 and Q2 in terms of Q0 from this equation? Can you quickly tell me how much it's going to be? Minus Q1. If I add these two, then I get minus Q1 is 5Q0. So Q1 turns out to be minus 5Q0. Am I right? Q2 then will turn out to be minus 8Q0. Q2 will turn out to be Q1 minus 3Q0. That means minus 8Q0 is Q2. Please plug in Q1 and Q2 in terms of Q0 so that Q0 can be cancelled from numerator and denominator, and tell me what's the value here. Plug in Q1 plus Q2. Q1 plus Q2 is minus 13Q0. And 2Q1 minus 10Q0 minus Q0, that is minus 11Q0. Yes or no? 13 by 11 Q0 will get cancelled, and the capacitance then turns out to be 13 by 11 microfarads between A and B. This is 13 by 11 microfarads between A and B. Which loop, my friend? This. अच्छा मेरे भाई वही लिया actually. तुम सोचो. This minus V equal to 0. So V equal to this plus this, isn't it? वही तो. Yes, you could have, but then why do you want to bring in V, yaar? Will it make life any better if you bring in V? Okay, you do that. So you could have taken any loop. KVL will apply. Q1 by 1 plus Q1 minus Q0 by 1 minus V equal to 0. Then what will it do? And then you take this. I'm also saying that only. A, P, B, A. Oh, A, P, B, Q, A. Yes. Oh, just this. This rhombus, right? Yes. This. In fact, I'll tell you what. If you add these two equations, you will get the equation for this periphery. Check that out. I challenge. If you add these two equations, you will get the equation for this. Because this element, in this loop, this element you have gone from here to here. And in this, you have gone from here to here. When you add the two equations, this will get cancelled, and you will have this going on for you. You will have the same equation, does not matter. You will not get any independent equations. There will be only these two independent equations. Anything else will only be a linear combination of these two equations, no matter what your choice of loop is. If you add the two equations that I've got, you will get the same equation as the equation that you get by applying KVL to this periphery. Rest assured. All's good, right? And then what would it do to you, my friend? कहाँ से यार? ये तो आसपास रहेगा. वन और वन पैरेलल में कैसे भाई? पैरेलल ले लेते तो क्या होता? ये पी क्यू तो इससे अलग ही रहता ना. शुरू से ही ले रहे. मैं शुरू से ही बोल रहा हूं मेरे भाई, कोनो फर्क नहीं पड़ेगा. कहां से बैलेंस व्हीटस्टोन ब्रिज में? मैं तुम एक को उठा के पॉकेट में रख लोगे, उसको बैलेंस व्हीटस्टोन ब्रिज बना दोगे, बाद में जाके इसको यहां पे सल्टा दोगे. ऐसे थोड़ी होता है गुरु. तुम वही क्यों? ये दो में से एक को बेटा पॉकेट में घुसा दिया पैरेलल वाला, और बोला अब तो ससुरा बैलेंस व्हीटस्टोन ब्रिज हो गया. नो माय फ्रेंड. तब हम इतना मेहनत क्यों करते? नहीं, see, it's a good idea. Wish it was like that. Life would have been so much easier. You can't do that, huh? Matlab, in an electrical circuit, you can't do this. This is too much of luxury to afford. You take one element, keep it in the pocket. Simplify matters there and वापस वहां पे dump कर दो. फिर बोलो ये है. नहीं करना, हाँ? होने से बहुत अच्छा रहता, लेकिन if that was the case, it would have been simply wondrous. So far, so good, right? Now, let me look at number 4. No. See, okay, ask all questions you can. Please don't feel deprived. He's saying, if I have taken this clockwise, do I need to take this clockwise? Not at all. You can take this clockwise, this anti-clockwise. You can go into a loop like this, any loop. Since, see, if you took this anti-clockwise, suppose instead of taking this clockwise, you had taken this anti-clockwise, then the equation you would have got is Q2 minus Q1 is minus 3Q0 is the equation that you will get. Do you realize that? Take in any sense you like. If one loop has been taken clockwise, the other loop is not married to that direction. You can take any sense. It will make sense. Clear? Yes, please. Look at number 3, 2 part 3. Let's look at 2 part 3 then. Hello? Now, look at this circuit. I want to find the equivalent capacitance between A and B. I want to be able to find equivalent capacitance between A and B of this network. Again, I'm going to imagine a hypothetical battery to be connected between A and B, isn't it? Imagine a hypothetical battery to be connected between A and B. and say there is a charge Q flowing through the battery. There is a charge Q flowing through the battery. That charge Q would get delegated into three constituents, Q1, Q2 and Q3. Say Q1 comes down here, Q2 deposits on this, and Q3 deposits on this. Yes or no? That means from B, I have sourced Q1 plus Q2 plus Q3. Must have flowed through the battery. So the equivalent capacitance is going to be what? Q1 plus Q2 plus Q3 divided by V. Right? V computed in any legitimate manner that I want. Now I make a statement and see if you find sense in that. I claim that this will be minus Q1, I claim that this will be minus Q2, and I claim that this will be minus Q3. I claim this. Not sure? Not sure now? No, this could have been minus Q1 plus delta Q. This could have been minus Q2 minus delta Q. That could also have been possible, isn't it? I mean, if this was 1, 2 and 3 microcoulombs, the total should have been 6. Why do you think I have minus 1, minus 2 and minus 3 here? That has to be thought of. This is about an observation. This is about an observation. Okay, listen to me. We're going to deploy this observation time and again, so give it a thought. See, if the terminals of the battery were like this, plus and minus, then this would be Q1, Q2 and Q3. If I reverse the terminals of the battery, then realize, because see, this one essentially will be the same as this one, this 2 would be the same as this 2, this 3 be the same as this 3. The circuit will become the same. There would be symmetry. There would be symmetry, right? This would become plus Q1, this would become plus Q2, and this will become plus Q3 if I reverse the terminal of the battery. Yes or no? Now, if you didn't believe that, suppose on reversing the terminals of the battery, this was, say, Q1 prime, this was Q2 prime, and this was Q3 prime. Q3 prime, on reversing the terminals of the battery, right? Now, this would have been actually Q1, Q2 and Q3 on reversing the terminal. If this was Q1, Q2, Q3 on reversing the terminals of the battery, this capacitance is what this was earlier, this capacitance is what this was earlier, this capacitance is what this was earlier. Yes or no? See, if this was positive, this was negative, we had Q1, Q2 and Q3. If I reverse the terminals of the battery, then whatever you saw of this capacitance earlier will now be witnessed of this capacitance. Whatever was this will now be this. Whatever was this will now be this. See, 1, 2, 3, 1, 2, 3. This is how everything else remains the same. Do you see there is symmetry there? What? So if I reverse the terminals of the battery, this would be Q1, this will be Q2, and this will be Q3. Now there are two circuits. Say one with this terminal and one with reverse terminal. If I superimpose the two circuits, then this will become 0, plus V and minus V, this will become 0. Then on superimposing the two, this would become 0. This will become 0, this will become 0, the net charge will be 0 on any plate on superimposing the two circuits. That means the circuit with terminals with this being positive and this being negative, when superimposed with this circuit, gives me 0 here and this 0 here. That means if this was positive and this was negative, then this should have been minus q1, this should have been minus q2, and this should have been minus q3. So that when I superimpose with polarities reverse both the circuits, they turn out to be 0. That means if essentially this was plus and this was minus, then this should have been minus q1, this should have been minus q2, and this should have been minus q3. Yes or no? Repeat. See, there are two circuits. Listen to me carefully. This is the battery with polarities like this. This is V volts, right? What that has resulted in is this 1 microfarad, this 2 microfarad, and this 3 microfarad having Q1, Q2, and Q3. All right. And this was 1, 2, and 3. And then there was 1, 2, and 3 with, say, charge Q1 prime, Q2 prime, and Q3 prime, say. With the original state, 1, 2, and 3 had, say, Q1 prime, Q2 prime, and Q3 prime, right? Now, reverse the polarities. Reverse the polarity. So, essentially I want to establish that Q1 prime must be minus Q1, Q2 prime must be minus Q2, Q3 prime must be minus Q3. That's my objective in this state, Now, when I reverse the polarity, whatever you saw of this capacitance will become of this capacitance. Whatever you saw of this capacitance will become of this capacitance. Whatever you saw of this 3 will become of this 3. Yes or no? That means now, when I am reversing the polarity, this would be Q1, this would be 1 microfarad Q1, this one is the same as this one. Then this would be the second capacitor Q2. This would be the third capacitor Q3. Yes or no? These 3 capacitors would now be Q1, Q2, and Q3 on reversing the polarities. Yes or no? Now take this circuit and place it over this. I want to find Q1 prime, Q2 prime, and Q3 prime. When I superimpose these two, then this V will cancel with this V, 0. So all charges will be 0. That means on superimposing, Q1 prime plus Q1 must be 0. Q2 prime plus Q2 must be 0. Q3 prime plus Q3 must be 0. That means Q1 prime must be minus Q1. Q2 prime must be minus Q2. Q3 prime must be minus Q3. Are you all fine with this idea? And therefore, if this was Q1, Q2, Q3, this will be minus Q1, minus Q2, and minus Q3 as suggested. Does this bother you, or are you fine with this? Very good. Can I remove this? Yeah, please copy this. Take this circuit, place it over this. This V will become 0. All charges will become 0. Right? Right? This too. See, look at the symmetry. Look at the symmetry. You interchange these two. Will anything change? Nothing will change. So there is symmetry in that context. No, it will change. Then there won't be symmetry. Then this will not be minus Q1, minus Q2, and minus Q3. That will not happen. It will not have that symmetry. If this was 4 and this was 8, then it gets disturbed. Right? Now, so I'm deploying symmetry actually. Now, good. So we have minus Q1, minus Q2, and minus Q3, minus Q1, minus Q2, minus Q3 here. Now notice then that if this is Q1, how much will this be? Minus Q1, right? If this is minus Q3, how much will this be? Q3. Now this is minus Q1, this is Q3. These three are electrically isolated. So the net charge on these three put together must be 0. That means the charge here must be Q1 minus Q3. The charge here must be Q1 minus Q3. Right? And therefore the charge here must be Q3 minus Q1. Q1. Now, if this is Q3, how much is this? Minus Q3. If this is minus Q1, how much must this be? Q1. Now these three are electrically isolated. They are only communicating with each other. This plate and this plate. Together they must have no net charge. So if this is minus Q3, this is Q1, this must be Q3 minus Q1. No, dude. Q3 minus Q1. Q3 minus Q1. Net will become 0. So if this is Q3 minus Q1, this will be Q1 minus Q3. If this is minus Q2, how much must this be? Q2. If this is Q2, how much must this be? Minus Q2. And realize these four plates are talking to each other and they have no net charge. See, this plate, and this plate, 0 charge. Yes or no? Right? Now, all that you need to do is, you want to be able to apply, say, KVL to this loop and KVL to this loop. When you apply KVL to this loop, what is it that you get? This loop. Q1 by 1 plus Q1 by 1 plus Q1 minus Q3 by 4 minus Q2 by 2 equal to 0. Yes or no? You can simplify this. 4Q1 plus Q1 minus Q3 minus 2Q2 equal to 0. Or we have 5Q1 minus 2Q2 minus Q3 equal to 0 when you apply KVL to the upper loop. Right? Now when you apply KVL to the lower loop, Q2 by 2, going Q2 by 2, Q1 minus Q3 by 4, by 4 minus Q3 by 3 equal to 0. Yes or no? So if I multiply by 12, I get 6, 3 minus 4Q3 equal to 0. This is what I get. So this gives me like a 3Q1 plus 6Q2 minus 7Q3 equal to 0. Equation 2. Yes or no? Clear? These two equations? Clear? So essentially, if you like, you can transpose Q3 here, transpose Q3 here, solve Q1 and Q2 in terms of Q3. You can solve for Q1 and Q2 in terms of Q3, right? I'm not wasting time on that anymore. Now to find the capacitance of this arrangement between A and B, to be able to find the capacitance of this arrangement between A and B, the total charge flowing through the battery, which is Q1 plus Q2 plus Q3 divided by the potential difference between A and B. Now, from A to B, I can go any way I like. For example, to compute the potential, right? I can go this way. For example, that's the best thing to do, right? So Q1 by 1, I'm going from A to B to compute the potential drop. Drop across this plus drop across this is going to be the total drop across A and B. Or if you want to make it complicated, I have no problem. You can go from A to B like this. B. Right? You could do that. So the drop from A to B is going to be drop across this, which is Q1 by 1 plus Q3 by 3. Now, you can solve for Q1 and Q2 in terms of Q3. So Q1 and Q2 could be plugged in terms of Q3. Q3 will get cancelled and you will have a pure number, positive number emerging out of this computation. And that's going to be the capacitance of this arrangement between A and B. That's the greatest extent of complication. Now, see, I applied to this loop, but I didn't apply to this loop and didn't apply to this loop. Reason? Because the KVL applied to this loop will be the same as the KVL I applied to this loop. This loop is the same as this loop, and this loop is the same as this loop. So these are not independent loops. I have already deployed symmetry where application of KVL to this loop and this loop will turn out to be the same. Symmetry has caused it to be such. Fine. Now, your attention please. So now we have the simplest member of this family, part 4, where we have a circuit like this. Damn thing, shut up! Hello? I want to find the equivalent capacitance of this arrangement between points A and B. I want to be able to find the equivalent capacitance between points A and B. See, look at this. These two plates are connected by a conductor. So they'll be at the same potential. If they'll be at the same potential, the electric field between these two plates is going to be 0. That means then this capacitor is a non-entity here. If it's a non-entity, why allow it to stay put? Shun it. Remove it, isn't it? Now you have C and C in parallel, that makes it 2C. Right? Equivalent capacitance between A and B is going to be 2C.